Alright, in this video we're going to pick up where we left off last time. You already know about wires, how to change their resistivity, resistors, how to change their resistance, batteries, how to change their EMF and power supply and internal resistance, how to add switches in. Now what we're going to do is we're going to have a way to measure stuff, and so that's using these tools like the voltmeter and the ammeter. And there's different ways that we add in the voltmeter and the ammeter. And so I'm just going to make this a fairly simple circuit for the start. I'll put in actually let me just make this a little bit longer. Put in the switch so that I can turn this on and off. And lastly, what we're going to do is put in an ammeter. So I now have this ammeter tool that I can add in, and I'll connect it all up with a wire. Okay, so it's all connected up, and all I have to do now is throw the switch on, and we can see that we get progression through the circuit. Actually, what I think I'd like to do is let's get a light bulb so that we can see this in a more visually exciting way. Stop that. Seriously. Okay. Alright, now when I throw the switch on, we see that there is current going through the circuit. Now the way that an ammeter works is you have to connect it in the circuit. It has to be part of the circuit, because what it's doing is, if you remember how we initially defined current, basically what it's doing is it's just counting up the number of charges that are going through it. And it obviously can't give you an accurate reading unless it's part of the circuit. One thing that you can't do here is change the resistance. What we want is for our ammeter to have essentially zero resistance. And if you think about this for a moment, I think you'll see why. If it has resistance, then that means it's going to affect the amount of charge that flows given a particular battery. And we don't want that to happen. Now in actuality, we can't achieve that. We can't make it so that it has zero resistance, but we can make it so that it has pretty close to zero resistance. So the hope is, just like the wires, how we often treat the wires as having zero resistance, we hope that the ammeter also has zero resistance, at least in comparison to the resistance of the light bulb. So I can turn that on, and you see that it gives me a reading of 9 amps. Turn it off. I'm sorry, 0.9 amps. So we can turn it on and off. If I go ahead and I change the voltage here, so it's at 9 volts. Let's change it to go wild and do 10 volts. Now I connect this, and we have 1 amp. Okay. The reason why we're getting these particular numbers is because the resistance of this light bulb is 10 ohms. So with 10 amps, with a resistance of 10 ohms, we get 1 amp of current out. So that's one of the major new components that we're going to be looking at. And I can move this actually to anywhere in the circuit that I want. I can go ahead and split that junction. I can remove that and add an ammeter in down here. Okay, and when I put the switch on, once again, am I not connected? Apparently I am not connected. I'm not sure where I'm not connected. It does appear as though everything is connected. So this is a little bit vexing. Let me pause the recording and see if I can fix this. Okay, I have done it. Apparently all that I needed to do was click the pause button and then click the play button again. So we have this pause and play, and you can also step through things if you want to. And when I have it on the pause, if I go like this, nothing happens. But sometimes it also seems if you move parts about, you need to repause, and then you can hit the play button, and all of a sudden things happen. When it's in pause mode, you can click things forward step by step. Not sure why you want to, but you can. This might actually be more useful when we're doing alternating current, which won't be for almost a year, maybe 8 months or something like that. But in any case, we're going again, and you can see that the ammeter position does not seem to matter, whether it's at the tail end or whether it's at the front end, and you can see that just by the motion of the charges. They are all moving at basically the same rate. Now we have another tool that we can use, and it's called a voltmeter. Right now the voltmeter is not sure what to do. It likes to grab onto things though. These are called probes. Typically you put this towards the more positive end, so let's just stick it on the positive end of the battery, and we'll stick this one at the negative end of the battery. And what it's doing is it's measuring the voltage drop, or the potential drop, from the positive end to the negative end of the battery. And no surprise, it's 10. We've dropped by 10. If I reverse these around, the voltage drop is negative 10. And it's just saying that you actually are climbing up if you go from this end to that end. So we have a minus 10 versus the plus 10, depending on how we do it. Now remember, the wires have no resistance. So let's say that I go from, bear in mind that conventional current, and I'm going to hide these electrons for a second so it's not confusing. Conventional current is going clockwise in this case. So if I go, say, from here to there, from this wire, from the start to the end of it, then what we get is simply 0, because there's no resistivity in that wire. Now if I change that, as I increase the resistivity of the wire, you're going to notice a couple things happening. One thing that happened is that the current is less, and let's just show those electrons so you can see they're fairly lively and they become a little bit more sluggish. What we're seeing then is the current goes down because the charges aren't moving as rapidly, and the voltage, in other words the energy that the charges have to use up across this wire element, increases. So this is measuring how much energy they have to use up across a particular element. If I go ahead and put it across the ammeter, I get 0. Oops, if I don't actually put it on the ammeter, I get not sure. I get 0 in that case. If I put it somewhere along this wire, you can see that it's using up voltage again. Okay? And if I put it over here on the exit side of the terminal, we get this big jump. And what I'm going to do is actually reduce the resistivity of the wires to 0. And now you can see that I have a 10 drop as I go along here. If I move it to this side of the light bulb, I get a 0 drop. If I move it to this side, I get a 10 drop. So I can just zero in on exactly where I'm losing this energy. And it turns out that I'm losing it right in these filaments, basically. Okay? So right in the side of the light bulb here is where I'm losing all of the energy. And you can see that, actually, it's coming out as light. If I go over to this side, so everything's on the exit end of the light bulb, I have 0 voltage again. This isn't to say that there's 0 energy, it's just that there's 0 change in the energy that's involved. So if I have the probes on opposite sides of the light bulb, we get a voltage drop of 10. Whether it's at the battery or whether I bring it all the way over, we're not sure what's going on inside the ammeter apparently. If I bring it all the way up to the entry point of the light bulb, somewhere on the exit side, I get a 10 volt drop. That's because we have a light bulb there to use all of that up. Alright, and just to finish this up then, I just have a single battery with the voltmeter connected, and you can see that the voltage drop is 9 volts. One of the things that's different is that I didn't, compared to an ammeter, is that I did not put this in as part of the circuit in the previous case. That's because we're measuring the voltage across. Now if the voltmeter is the only element, then what happens is the current has no choice but to go through the voltmeter. And so what's happening is it's actually reading the voltage drop across itself when I only have that connected. When I have other elements, unlike the ammeter, what we want is we want the voltmeter to actually have a huge resistance. And this is so that current does not actually go through it. It looks at it as something that it doesn't want to go through. Now, I should be careful when I say that. Very, very little current. We want very, very little current to go through there, because otherwise it siphons off what's happening when we try to measure the current. So those are things that we need to be careful of and understanding, and they're things that I'll reiterate in the future as well as we study these things more. What I would recommend now is that you go ahead and play around with this. Maybe try some other combinations of things and see how that works. Learn how you can set things up and that type of a thing. What we'll be doing is I'll be giving you some more specific experiments in the future, in the next couple of weeks, for you to try out and see what happens.